looks like I've actually remembered how to stream this time, so hopefully everything will go well.
We didn't hear that. No audio. Oh. There you go.
Ooh, complex numbers. I like those. Okay. So that's a annoying input format. I think this works. Sure. Yeah, that seems fine. So we do 10 steps of, or sorry, 3 cycles of r multiplied by itself, r divided by that, and then r plus equals a. I don't actually know if this will work. Are we supposed to round? Floor, okay. I don't actually know if... I think we have to do... I think we have to do this. $25,974.5. How's it telling us to do division? I don't think that's how you're supposed to do it, but okay. Sure, that gives us the correct answer at least. These formats are annoying, but sure. Okay. Part 2 says that we have a grid and A now defines the top left corner and the bottom right corner is 1,000 above that. Okay. Oh, this is rather complicated. Okay. I think I understand. So basically, we have a bunch of points. So for real in range 0 to 100,000, although we want it to be inclusive, so let's just do range 101 for imagining range 101. The point starts out at a dot real plus real times 10 plus a dot image plus image times 10 times j. I think that's how it works. So we start with that, then that looks roughly correct to me. The last 5 points in the last row should go up to 300 plus 6. No, that's not right. Ah, yes. That should be a thing in the first one as well, I suppose. Okay, that looks right. And then for each point, in order to determine whether or not it should be engraved, we do a similar thing as last time where we set r equal to 0, and then we do 100 cycles. R times equals itself. R equals r dot real divided by 100,000. And then r plus equals p, and if either is out of the range of 1 million, so if then we continue. Otherwise, if we fall out of this range, then we break. And if we didn't break, then that means we went through all 100 cycles without exceeding the range, so we do count plus equals 1. And then theoretically, this should give us a value of 4076. And this gives us our answer of 1259. Excellent. Okay. Last part, symbol is too faint to clearly be visible. We can calculate a far more detailed grid with... I see. So, I see, okay. So we're enhancing the precision by basically increasing the amount of... Okay. I saw that the first one was a bit slow, so I'm sure there's probably a better way of doing this, but during the contest it'll be faster to just brute force it anyway. Hopefully this doesn't take too long. I'm gonna run it in parallel just on the actual test case, but and yes, I am aware this is just a Mandelbrot set, or at least I'm pretty sure it is, but I don't quite remember if there is a way to optimize that. Okay, 406954. That gives us our answer of 124041. Cool. Yeah, I think given that that didn't take too long to run, I'm not too convinced it's worth optimizing it any further. Let me quickly think over if there's any easy optimizations for this though. Yeah, no, I'm not convinced there's too much of a better way around this. Okay. Let's move on to the explaining part of this then. Okay. So gathering the input for this is not too complicated. The way I did it is rather bad. What we can do instead is instead of using regex to parse out the numbers, we can just say that we take the input and we remove the a equals open bracket and the last close bracket and then split it on commas. We can do real image equals map int over these two. And then once we have that, we can do a equals real plus image times 1j. Now the first part is relatively straightforward. We start with our result equal to 0. So since Python has built-in complex numbers, we can just use those directly. Although the way that we are doing division here is a bit annoying with built-in imaginary numbers, it still saves a lot of time to use them because otherwise you'd have to write out the multiplication manually, and that gets a bit more annoying. So I find that it still makes sense to use them here, although we can define a division function to make it a bit easier. What we can do is we are basically dividing the real values and the imaginary values separately and then recombining them into an imaginary number. So we can return x.real divided by y.real plus x.image divided by y.image times 1j. And we use int here to truncate the fractional component, which is what it's asking us to do here. And so we start with the result equal to 0 and then do 3 cycles of multiplying the result by itself, dividing the result by 10 plus 10i, and then adding a to the result. And the output that it wants here is to have the real and imaginary components separated by a comma within square brackets, which is slightly annoying, but we can use format strings to template that pretty easily. We just do a square bracket, the integer real component, a comma, the integer imaginary component, and then a closing square bracket. And so that'll get us what we want for part 1. We can carry all of this over to part 2, the parsing and division utility function. And what we're doing here is we want to count the number of points within a certain range that satisfy a condition. I mentioned the Mandelbrot set earlier on stream. If you're not familiar with that, it's a fractal that's defined using complex numbers. So it's defined on a complex plane, and essentially the idea is for each point, we determine whether it's in the set or outside of the set using something very similar to this. So what we're doing here is we're doing a bunch of cycles of starting with a result of 0. We multiply the result by itself divided by some amount. This amount is basically just a scalar to scale the size of the set. And then we add the point that's currently being checked. And so what we're doing is, given a certain point, we take a result starting at 0, multiply it by itself, divide it by some scalar, or we can also just ignore the scalar, and then we add the point, and then we square this again and add the point. So we're basically taking the point and mapping it to, given a result, we're mapping it to the result squared plus the point, and then we're feeding this into itself repeatedly. The Mandelbrot set basically asks, is this a convergent value? So if we keep doing this repetitively, does it diverge to infinity, or does it stay at some constant value, or does it converge to 0? If it converges, it's within the set, and if it diverges, it's outside of the set. And that's why we have this condition where if at any point it exceeds this range, we consider it to be outside of the set. This is technically not a perfect way to check if a value converges or diverges, but Mandelbrot sets are usually calculated using an algebraic approximation like this. This isn't too relevant to the actual problem itself because I don't believe there's anything in particular you can take advantage of to simplify this process, but it is interesting to see where this concept originates from. And so once we have our A value, we want to look at the values ranging from A to 1,000 by 1,000 to its bottom right, so positive in either direction. And so we can loop through the offsets here. What we can also do is loop like so. And what this basically means is we're looping from 0 up to but not including 1,010, stepping by 10 each time. And so that removes the need to do the times 10 here, and is a bit more straightforward. So given a starting point P, which is being examined for inclusion in the set, the rest of this is all fairly straightforward. It comes straight from the first part. Like so. And then the only part that's a bit weird is this check. I'll write it out to be a bit more straightforward. So we can keep track of a variable called, let's call it exceeded, because we're checking if something's exceeded the range. If at any point the either component exceeds 1,000,000 or is less than negative 1,000,000, which we can also do by just taking the absolute value and checking if the absolute value exceeds 1,000,000. Then we set exceeded to true and exit the loop. And then at the end of the loop, we can count if we did not exceed the range, then we increment the count of the number of points included. The notation I've used here for else, I have a short on YouTube explaining this concept. Basically, if we break, then we skip the else block as well, and if we don't break, then at the end of the for loop's usual execution, we'll go to the else block. So we can also do this and remove the need for the exceeded variable altogether. That's what I was doing the first time, but in the interest of clarity, this might make a bit more sense. And so that'll get us our part 2. You'll notice that it takes a second to run. Not a big deal for part 2, but with part 3, what we're essentially doing is just removing the skip by 10 each time. And so for part 3, the performance does end up becoming a bit of a problem. Do let me know if any of you have any ideas for ways to optimize this. I can't really think of any off the top of my head that are like simple enough to justify using here, but I very well could be missing something. It's been a while since I've worked with complex numbers, so I might be a bit rusty with them. But if we wait for this to run for a bit, we should get the same answer as before. Yeah, perfect. So relatively straightforward problem with Python complex numbers. If you don't have complex numbers, then it will take you a bit to, I guess it wouldn't take too long to write this out. Just to demonstrate for anyone who's mainly using other programming languages, we don't need to use Python's imaginary numbers. So what we could do instead is something like we could just define utility functions. Like so. The only one that is really notable is the multiplication one. But it's not too bad. You can just copy what's being done. Like since they tell you how to multiply complex numbers, you can just copy this directly. If I knew how to type, that is. And then the division function is just about as simple since we had to write a division function anyway. Like so. And then we could write it out like this. Like it's not too much more complicated, to be honest. Did I copy this line over wrong? Ah, I did actually copy it over wrong. Oops. I thought they were using x1, x2 for... I thought they were using x for the first variable and y for the second one. I didn't realize they were using 1 for the first variable and 2 for the second one. Okay. Learning how to read continues to be important for challenges like this. Okay, this should hopefully work. Yeah, there we go. Okay. So yeah, if you don't have complex numbers in your language, it isn't too much effort to write out the utility functions to work with them, but it is obviously convenient to have them in your language and does make it a lot faster, so that's why I continue to use Python. I found complex numbers to be honestly one of the main reasons I use Python over other languages for contests like this. It's also just a lot more convenient for like input formatting and stuff, but complex numbers is definitely an advantage for anything that, like for the few challenges you get that explicitly use complex numbers, but also for a couple of cases where you have coordinates that you need to like add or subtract and rotate as well. But yeah, very interesting problem 2. Let's see how we're doing overall. Cool, pretty good. Okay, well, in that case, excited to see what's next. Thank you all for watching, and I'll catch you on tomorrow's stream.